Okay, let's unpack this. That blinding flash that just splits the sky, right? And then that earth-shaking rumble lightning. It's this raw, kind of untamed power that has fascinated and frankly frightened us for ages. They're all focused on this core question. What exactly is a lightning strike? So our mission today is to plunge into these sources, sort of cut through the mystery, and really uncover the surprising science behind this, electrifying event.
Electrifying, nice one.
So here's where it gets really interesting. When we actually see that flash, what's really going on up there?
Well, it's pretty remarkable when you think about it. What seems like just one instantaneous burst is actually quite an intricate process.
Okay.
Our sources define a lightning strike as basically an electrical discharge that happens between the atmosphere, usually from those huge cumulonimbus, thunderhead clouds in the ground.
Big anvils.
Exactly. And it's important to remember, this is a specific type of lightning event. We see loads of flashes happening within clouds or between different clouds.
Yeah.
But a strike, that's when the energy finds a path all the way down to the Earth's surface.
Gotcha. So it's that direct connection, sky to ground. And I was really struck by the fact that while it looks like one big solid bolt, it's actually this multi-stage thing that's over in like a blink of an eye, a tiny fraction of a second. Plus, get this, that incredibly bright channel we actually see is only about an inch in diameter. It looks so much bigger.
You're absolutely right. The sheer intensity of the light just makes it appear much more substantial than it actually is. It's an illusion, sort of.
Wow.
And the dramatic boom we always associate with lightning, the thunder, that's a direct result of this rapid discharge.
Okay.
The huge amount of energy suddenly heats the air in that narrow channel to an incredibly high temperature. We're talking unbelievably hot.
Right.
And that causes the air to expand explosively, creating a shock wave that we hear as sound.
Flash first, then the bang. Because light travels faster than sound. Makes sense.
Precisely.
And it's interesting, the sources mention how different cultures recognize this. They have Falep just for the flash, and Fafa specifically for the ground strike. It shows how fundamental it is, Now, these sources also break down lightning into different types. It's not just cloud to ground, is it?
Not at all. And understanding these different types really helps put cloud to ground strikes into perspective. It's just one piece of a bigger atmospheric electricity puzzle.
Okay, so what are the others?
Well, you've got the classic cloud to ground, or CG. That's the one everyone pictures hitting the Earth.
Right.
Then there's ground to cloud, GC. That's less common, and it actually shoots upwards from tall things like skyscrapers or towers.
Oh, okay. Upwards.
Yep. But here's the kicker. The vast majority, like most lightning events, are actually intracloud, IC. They happen entirely within one single thundercloud.
So that flickering you see inside the storm.
That's probably it. And you also have cloud to cloud, CC, where discharges jump between separate clouds.
So only about, 25% of all lightning worldwide actually hits the ground or something on it?
That's what the data suggests, yeah. Roughly 25% are these atmosphere-to-earth strikes.
That really changes how you think about it. Still, that 25% is undeniably powerful. And speaking of power, wow. The numbers mentioned in these sources are just staggering.
They really are. It's an immense display of energy. We're talking extreme heat, first off, up to 30,000 degrees Celsius.
30,000 C. That's...
To give you some context, that's nearly 5 times hotter than the surface of the sun.
That's insane, all packed into that tiny little channel.
Exactly. Then you look at the electrical side. Voltage in the millions. One source even mentions over 20 million volts.
Millions of volts.
And current in the thousands of amps. Compare that to your home outlet, maybe 120 volts, 15 amps. It's a completely different scale of power.
A completely different universe almost. And the speed of it all, that matters too, right? The rapid rise time of the current.
Absolutely critical. Think about flipping a light switch. The current builds up relatively slowly. Lightning. It's like instantly throwing a massive switch to full power. Boom!
Right.
That rapid energy transfer is key to its destructive force. And when it hits something with moisture, like a tree, that intense heat instantly boils the water inside to steam, flash boiling, which creates this explosive force that can literally shatter wood, even rock sometimes. It's just raw energy unleashed.
That image of a tree just exploding. That really drives home the danger. So how does this raw power translate into danger for us, for living things? It's not just about getting hit directly, is it?
No, and that's a crucial point for safety. A direct strike, where a person becomes part of that main channel, is often fatal, obviously, due to the sheer energy involved.
Right.
But it's not the only way. There's contact injury touching something that gets struck, like a metal fence or railing.
Yeah.
Then there's side splash. The current can actually jump from the main strike path to a nearby person or object.
Jump, like arc across.
Exactly. And don't forget blast injuries from the actual shockwave of the thunder itself. Less common for serious injury, but possible.
And then there's ground current. The sources highlight this one-step potential, they call it. Sounds like it accounts for a lot of injuries and even deaths.
It really does. It's a major, often underestimated hazard. When lightning hits the ground, the electricity doesn't just stop. It spreads out through the earth.
Like ripples in a pond.
Good analogy, yeah, like ripples. Now, the ground isn't a perfect conductor. It has resistance. So you get a difference in electrical potential voltage between 2 points on the ground near the strike.
Okay.
If you're standing with your feet apart, even a short distance, that voltage difference can drive a current up one leg, through your body crucially, often across the heart and down the other leg.
Oh, wow. So your own legs complete the circuit, even if you weren't hit directly at all.
Precisely. You could be meters away from the actual strike point and still suffer severe injury or death from step potential.
That's sobering. You really have to be aware of the ground itself. The notes also mention EMP's electromagnetic pulses.
Right. That powerful electrical discharge creates this brief but intense burst of electromagnetic energy, an EMP.
And that causes problems how?
Well, it might not be as immediately life-threatening as a direct hit, but it can induce sudden voltage surges in electrical wires and systems.
Like frying electronics.
Exactly. It can damage sensitive electronics, potentially interfere with medical devices like pacemakers, or even damage building wiring. It's another layer of potential impact.
But the dangers are really varied. Direct hits, touching things, side splashes, the shockwave, ground current, EMPs. And the stats are pretty grim. Fatalities in, 10-30% of cases?
Around that, yes. And even survivors often face serious long-term neurological or physical injuries. Burns, memory issues, chronic pain. It's not something to trifle with.
Definitely not. And beyond people, the impact on nature is huge too, isn't it?
Oh, absolutely. We mentioned trees exploding from the sap boiling.
Yeah.
Lightning is also a major natural cause of wildfires, especially in dry areas.
Right.
It literally ignites vegetation.
Right.
We see rocks getting shattered.
Yeah.
And those examples in the sources are heartbreaking. Hundreds of reindeer in Norway, cows in Australia killed simultaneously by ground currents from a single strike.
Just wiped out by the step potential spreading through the ground. Incredible. The briefing doc even mentions things like church steeples exploding back in the day because they stored gunpowder.
Right, before lightning rods were understood.
Or modern music festivals like Rock am Ring getting canceled because of severe storm warnings. It's a consistent threat.
It really is.
Yeah.
Which brings us, naturally, to protection and mitigation. How do we deal with this?
Yeah, what can we actually do about it?
Well, we've developed quite sophisticated lightning protection systems. Lightning rods are the classic example, those metal spikes on buildings.
How do they work exactly? Do they attract lightning?
Not really attract, more like. Provide an easy path. They offer a low-resistance roof for the lightning current to travel safely down into the ground, bypassing the building structure itself. Protects the building from catching fire or structural damage.
Okay, so they guide it safely.
Exactly. And similarly, lightning arresters and surge protectors do the same job for our electrical grids and the wiring in our homes, protecting sensitive equipment from those EMP-induced surges we talked about.
Right, those little power strips people have. So these systems manage the energy. What about predicting it? You mentioned monitoring systems.
Yes, we have extensive networks now, both ground-based detectors and satellites, that track lightning activity over huge areas.
So they can tell us when a storm is coming?
They can tell us when and where lightning is currently happening and track the movement of storm cells. This allows for warnings about increased risk in certain areas. Very valuable.
But they can't predict the next strike.
No. Predicting the precise time and location of an individual lightning strike, that's still beyond us scientifically. We know the conditions are right, we know the storm is active, but pinpointing the exact spot, impossible right now.
Okay, so warnings help, but personal safety is still paramount when thunder starts rumbling. What are the key things you need to do?
Rule number 1, get inside. Seek shelter immediately in a substantial, fully enclosed building, or a hardtop car or a truck with the windows rolled up.
Why does a car work?
It acts like a Faraday cage. The metal body conducts the electricity around the outside, keeping the occupants inside safe. It's not the rubber tires, it's the metal shell.
Ah, okay. Good to know. And what should you avoid?
Definitely avoid open fields, hilltops, being near tall, isolated things like a single tree, metal structures like fences or bleachers, and absolutely stay out of water lakes, pools, the ocean.
Right, even small open shelters like picnic areas.
They offer very little protection. You're still exposed. Inside a proper building, you should also avoid contact with corded electrical appliances, and stay away from plumbing pipes can conduct electricity if the building is struck.
Okay. What about that lightning position if you're caught totally exposed? Crouching down.
Yes, if you absolutely cannot get to safe shelter, crouching low with your feet close together can minimize your contact with the ground and reduce the risk from ground current, that SEP potential, knees bent, feet touching if possible. But it's really a last resort, not a guarantee.
A last resort, okay. And you have to be wary of those bolts from the blue, right? Strikes that come out of nowhere.
Exactly. Lightning can travel horizontally for miles from the parent storm cloud and strike in an area where the sky overhead looks clear. So even if the main storm seems distant, the danger can still be present.
That's unnerving. The flash to boom count is useful, though, isn't it?
It is. It gives you a rough idea of distance. Count the seconds between the flash and the thunder. Every 5 seconds is about a mile away.
So if you count less than, say, 30 seconds.
That's 6 miles or less. You're definitely in the danger zone. Time to get inside immediately. When thunder roars, go indoors is the simple rule.
Good rule. Are there any immediate warning signs, like if a strike is really close?
Sometimes, yes. You might hear crackling sounds, feel your skin tingle, or your hair might literally stand on end due to the strong electrical field building up.
Whoa.
You might also see a faint blue glow around sharp metal objects that St. Elmo's fire. These are all urgent signs to take immediate action.
Okay. And crucially, if someone is struck, they don't hold a charge, right? You can help them.
Absolutely crucial point. A person struck by lightning does not retain an electrical charge. They are safe to touch, and immediate CPR or first aid can be life-saving. Don't hesitate to help.
Good. And finally, the danger doesn't end with the last thunderclap.
No, the risk remains significant for a while. The recommendation is to wait at least 30 minutes after the last sound of thunder before resuming outdoor activities.
30 minutes. Got it. So there's a lot we do know about lightning strikes and safety, but the sources also point out there are still mysteries, things science hasn't quite figured out.
Oh, definitely. It's quite humbling, actually. One of the biggest puzzles is how the discharge even gets started.
What do you mean?
Well, the electric fields we measure inside storm clouds often seem weaker than what our physics models say should be needed to break down the air's insulating properties and initiate that massive spark.
So how does it start?
That's the billion-dollar question.
Yeah.
One leading theory involves high-energy cosmic rays from outer space hitting the atmosphere. These particles might provide the initial seed of ionization needed to get the process going in those weaker fields, but it's still debated.
Cosmic rays triggering lightning. Wild. What else is mysterious?
There are phenomena like sprites and jets. These are huge, faint electrical discharges that shoot up from the tops of thunderclouds high into the upper atmosphere. We can see them from space, but we're still learning exactly how they form and what role they play.
Sprites and jets. Cool.
And then you see lightning in really unusual situations, like inside the ash plumes of erupting volcanoes, or within the massive smoke clouds generated by intense wildfires, powered cumulonimbus clouds. These extreme environments challenge our standard models.
So despite all our tech and knowledge about what a lightning strike is, nature still holds some cards close to its chest.
It certainly does. But it's not all danger and mystery. Your sources rightly point out some surprising, even beneficial aspects of lightning.
Beneficial? How can lightning be beneficial?
Well, this is pretty fascinating. Lightning is actually a vital natural fertilizer.
Fertilizer? Seriously?
Yes. The intense energy of a strike breaks apart the stable nitrogen gas molecules in the air, N2. These nitrogen atoms then combine with oxygen to form nitrates. These nitrates dissolve in raindrops, fall to the earth, and are absorbed by plants. It's a key part of the natural nitrogen cycle, essential for plant growth. Without lightning, there'd be significantly less usable nitrogen for life.
Wow, okay. Lightning fertilizes the planet. What else?
Well, it obviously occurs in thunderstorms, which are responsible for a lot of our rainfall. So it's intrinsically linked to water cycles. And it also produces small amounts of ozone. While ground-level ozone is a pollutant, ozone in the stratosphere is crucial for blocking harmful UV radiation. Lightning contributes a bit to that upper atmospheric chemistry.
Natural fertilizer, linked to rain, ozone production. That puts a different spin on it. Any other benefits?
Scientists study the extreme plasma created by lightning to learn more about physics under intense conditions. There's even research into possibly one day using lasers to guide lightning strikes safely, or maybe even harness some energy, though that's very speculative.
Harnessing lightning sounds like science fiction.
For now, yes. But the study continues, and beyond the science, think about the cultural impact. Lightning has been a source of awe and inspiration forever.
Yeah, absolutely. The sources mention ancient myths, Zeus with his thunderbolts, Thor with his hammer.
Indra in Hindu mythology, all powerful sky gods wielding lightning. It represented immense power, divine judgment, or creative force across many cultures.
Until science started figuring it out. Benjamin Franklin and his kite.
A pivotal moment, wasn't it? Demonstrating the electrical nature of lightning. That shift from pure myth to scientific inquiry is a huge part of the story of understanding what a lightning strike truly is.
It really is.
What's just fascinating here, I think, is how something so instantaneous, so fleeting, can have such profound and lasting effects, both dangerous and surprisingly life-giving, and how it's just woven itself into our history and understanding of the world.
So let's bring it back to you, the listener. As you think about the next thunderstorm rolling in, what does all this really mean for you? Hopefully, this deep dive into your sources has given you a much clearer picture of what a lightning strike actually is. This powerful, complex, electrical discharge connecting sky and earth. Still a bit mysterious in some ways.
Yeah.
We've looked at its incredible power, the very real dangers it poses through multiple different mechanisms, and crucially, the practical steps you can take to stay safe. But we've also uncovered these surprising benefits, the fertilization, the connection to rain, and its deep roots in our culture and history.
Maybe consider how this natural phenomenon, both feared and beneficial, continues to shape our world and how we understand it. Makes you wonder, what other powerful forces of nature might hold similar dualities, both destructive and somehow essential?
That's a great thought to end on. Thanks for taking this deep dive